Welcome back. Explicit Euler numerical integration is a process of generating a solution trajectory given an initial condition, and then stepping through taking each solution and a linearization about that point so that we take the rise over the run that is known by the ODE, multiplying by the small step size or run to get an incremental rise that would give us the next solution on that trajectory, and then using that in a recursive manner to generate the entire solution. We've used this so far for first order ODEs, both single and systems. The single differential equation we considered was the logistics equation, and when we wrote this in terms of the difference equations, we had that for our dependent variable y, looking very similar to what we'd expect exactly from the explicit Euler, but we didn't maybe mention at the time the equation that we're integrating to find t, so to speak, is just dt dt, which is of course 1. In that case, the derivative here being 1. T at I plus 1 equals ti plus 1 times h. That's exactly what we've been using to find the corresponding independent variable for each dependent variable as we were integrating this logistics equation. The same exact process basically was occurring for an explicit system where the system was really coupled, meaning that all of the derivatives depended on all of the dependent variables, such that we had to solve for all of the solutions x, y, and r simultaneously. And that means that we would take the solution at x, y r at the solution step I, and then to find that next solution at the ith plus 1 step, we would integrate all of the equations together in a single loop. So far, therefore, we've seen that Euler's method integrates first order ODEs. But what we really like to do is extend this to higher order ODEs, so that means systems where there's a derivative that is more than the first derivative. The way that we would do that is actually by writing it as a system of ODEs, and that might be easiest to see in terms of an example problem. So take a simple pendulum where we have a massless rod of length L with a mass m at the end. It's fixed, pinned at this point such that it's going to oscillate about it. Theta is going to be measured from the vertical, such that when theta is 0, we're at a stable equilibrium. When we initially displace our pendulum from that equilibrium and let it go, it will oscillate back and forth. If the only, in reality we'd have drag, but in this case the only real situation we're going to allow for is the mechanism due to gravity. So our Newton's second law is going to reduce down to a second order differential equation for theta, which is equal to minus g on L sine theta. We're going to have two initial conditions. We'll have the same number of initial conditions as we do the number of derivatives. So if we have a second derivative, we'll have two initial conditions. The initial condition on omega here basically is speaking about how fast we release this mass. So at time t equals 0, we could push it instead of just letting it fall. To write this as a system is pretty straightforward. We go ahead and create a solution vector, we'll call it y, where the first element of that vector is just the variable that is being differentiated, theta. The next element of that solution vector is going to be the first derivative. And that's all that we're going to have. We're going to have the same number of elements in the solution vector as we do derivatives. Then if we take the derivative of y, dy dt, the derivative of the first element is just going to be theta prime, which written in terms of our new solution vector is y2. The derivative of y2, which is theta prime, is going to be theta double prime, which is exactly what was defined for us by our ODE. In terms of our new solution vector, that's just going to be minus g on L sine y1. So when everything is said and done, we've got now a system of first order ordinary differential equations that's coupled, meaning that to know how y1 changes, I need to know what y2 is. How to know y2 changes, I need to know what y1 is. So it has to be integrated simultaneously. This is exactly like the SIR model, where we're going to use this variable f, it's a vector value function, to talk about the derivatives. And in general, those derivatives depend on every single one of the elements in the solution vector. So, in general, we could do this with any nth order ODE by just letting our solution vector equal to the independent variable, or excuse me, the dependent variable and all of its derivatives up to, but not including the nth. And then taking the derivative of this solution vector, relating the various elements to one another, where the last element is actually going to be simply the ODE that was initially given. So we can always rewrite a high order differential equation as a system of first-order differential equations, and then we can employ our numerical integration technique. It's worthwhile mentioning that the Euler's method is probably not the best to use for a pendulum because for oscillatory problems like this, it's numerically unstable, but it will work for us in this small case. And our purpose here in being able to move forward will be to write our equations in such a way and to code it up in MATLAB that we could use built-in numerical integrators later on. The first step, obviously, in solving it numerically is to non-dimensionalize it so that our values for theta and t are nicely sized. The way that we do that is first recognizing that theta itself is dimensionless because radians are an arc length over a length. And time is going to be in seconds, so we need to non-dimensionalize that, but as of yet we don't know what that characteristic constant time, Tc, that scaling should be. We'll let the problem determine it for us such that the mechanism of gravity acting on our system is going to be what determines the rate of acceleration, or the rate of the acceleration, So going ahead and plugging in for what t is in terms of Tc star, both in the ODE and in the initial conditions, and then simplifying the initial conditions first, we go ahead and take this Tc t star at equals 0 and simplify it to just t star equals 0, dividing through by Tc on both sides. We have another condition at t equals 0, but this is on omega. Omega is just d theta dt. So replacing t with Tc t star again and recognizing that Tc is a constant, bring it outside of the differential. And then going ahead and multiplying both sides by Tc, we end up with our dimensionless initial condition d theta dt star at t star equals 0 is just omega Tc. And that's important to recognize that we've changed to a certain extent the initial condition based upon the scaling, and it's clear that it will be dimensionless. Omega is an angular velocity, has units of 1 on seconds, so multiplying by characteristic time with seconds yields a dimensionless right-hand side here. Our ODE is a little bit more interesting. In the basement here for this second order ODE, we have a second order differential, and what that means is that Tc here is really being squared. So when we bring it out, we get 1 on Tc squared. We're going to isolate once again this derivative dimensionlessly by multiplying through by Tc squared, or dividing by the coefficient in front of the highest order derivative, and we're going to end up with d squared theta dt squared equals minus g Tc squared on L times sine theta. In this case, we can see that the mechanism of gravity over here has got this big coefficient sitting out in front of it. Sine theta is varying with theta, but g Tc squared on L is a constant. On the left-hand side, we have the time rate of change of the velocity, or we have the acceleration, and what's really determining that is this mechanism of gravity. So to have these two weighted such that gravity is able to effectively change the left-hand side, which has got a 1 in front of it, we're going to set the weighting on the right-hand side also equal to 1, and that's going to determine Tc for us to be square root of L on g, which has units of seconds, which we can validate that we've not made a mistake. And now our differential equation is dimensionless and simplified. There's really 2 pi groups left, the initial condition on theta and that on omega. We go ahead now and we can integrate this. We just take this second order ODE that's been simplified and we write it as a system. You might want to practice this. We can begin really by looking at the initial conditions, and they will help to elucidate really what our vector solution y ought to be. So the first component ought to be on theta, and the second component ought to be on d theta dt, or omega star. And so we've got our initial conditions set up now, where y1 is theta, y2 is just simply theta prime. Our second order differential equation now becomes d squared y1 dt squared equals minus sine of y1. And so we've replaced theta with y1 here. Writing that as a system, we're going to have dy dt, dy vector dt is just going to be y2, so the derivative of theta is y prime, which is y2, and the derivative of theta prime is theta prime, double prime, which is just minus sine y1. And so we've got our system of differential equations now, where we can really see that these derivatives can be written as a vector value function f that in general is dependent on all of the dependent variables y2 and y1, where the first element of that function is just y2 and the second element is minus sine y1. We're going to go ahead and use explicit Eulers on this, just as we have in the past, where we're going to use this function f in our code in a second. So it's useful to remember that we're going to use f to stand for the derivatives. And in general, f depends on all of the values of the solution vector. Note also that this is kind of interesting. Y is both squiggled and has an index. The index I here is for the time stepping. So if we were to color code this, make the I here the color red, we're going to see that we have one index that's going to indicate which time step we're on. But this squiggle underneath the Y indicates that this is actually more than one value. It's a vector of values, one for each first order differential equation, one for theta and one for theta prime. And so we are going to have actually another index. We might indicate it with J. And j can equal 1 or 2. If j equals 1, we're talking about the y1 equation, which is the equation for theta. And if we're talking about j being 2, we're talking about the y2 equation, which is the equation for omega. So let's go ahead and take a look at how this kind of comes together for us in MATLAB. First, we just did the most straightforward process that we possibly could, and I would just call your attention to the comments here as we go through that are in the MATLAB code. We're going to integrate the ordinary differential equations here dimensionlessly. So h here is 0.01, and it's technically dt star. It's dt on tc, so it's dimensionless. We have our theta naught and our omega naught, where we've set our initial velocity here to be 0, our initial time to be 0. And then we've gone through and solved it first on lines 7 and 8 here in a very simplistic way without using any arrays at all. So theta 1 here and omega 1, those are going to be the values at the time step that is stepped 1 away from the initial condition of theta 0 and omega 0. So we get theta 1 by taking theta naught plus its derivative omega naught times h. Similarly, omega 1 is from omega naught plus its derivative, which is minus sine theta naught times the time step h. So this could work. We could actually copy these lines, paste them again, and change all of the values. Here we change the naughts to 1s in the next line and the 1s to 2s, but that's really burdensome. A first step to make it better would be to use arrays to keep track of the time stepping. So theta 1 here, where the 1 is our initial value in the theta vector, we're going to assign that to theta naught. Omega 1 is the initial value in the omega vector, we're going to assign that to omega naught. And then at the first time step, we're just going to solve for the ith plus 1 point given the ith point, where in the first time step, we've set I equal to 1. And then we repeat that where we could set I equal to 2 to solve for the next time step, which would be theta 3 and omega 3. Taking a look at the output in the workspace here, we can see that eventually we got to a place where we were solving for arrays of theta and omega for t. Theta doesn't change very much initially because the value of the velocity is 0 initially, but it starts to change in that third time step, you can see, whereas omega starts changing immediately from 0. What we want to do is generalize this, and as you can see, we've already abstracted it so that it's really set up to be a loop. But the best way to make this abstraction really work so that we can use this with multiple equations in the future is to go ahead and rewrite theta and omega as elements of a solution vector y, as we saw on the previous page. So to make this transition, we really have to kind of incrementally slowly do this. And the first thing to note is that we're going to have indices here that really refer not to the time stepping. So y here is going to be, in general, a solution vector. The first row is theta and the second is omega. And that's the first step. And we're going to now have a y solution vector that is going to have rows and it will have columns. And each column will be for a different time step, I equals 1 or I equals 2. But the first row is going to be for our theta values, and the second row is going to be for our omega values. So our first ordinary differential equation, it takes d theta dt, dy1 dt is y2. It is omega. And dy2 dt, the second derivative of theta, is minus sine theta, or y1, and that is our ordinary differential equation. So going ahead and slowly developing this. We have our time step. We've got theta naught and omega naught and t naught, our initial conditions. We're going to set up our initial condition array here. The first element, the first row is theta naught. The second element is omega naught. So right now, y naught here, the 0 here is representing the time step. The indices will be row 1 or row 2, designating whether I'm dealing with theta values or omega values. At the first time step, so y1 here, the 1 in the variable name indicates that I'm at the first time step. y1, so this is going to be the first time step of what? The index here is a 1, that is our theta values. So the theta at the first time step after the initial condition is going to be equal to the y01, which is the theta at the initial condition, plus that derivative, which is omega at the initial condition, times h, and so forth. So what we are seeing here is that line 25 here is slowly incrementing what we've done in the past, so that we're now going to have the time step in the variable name. And what we'd like to do is move it out of the variable name, like we did up here. It was in the variable name. We'd like to move it out of the variable name and into the actual matrix. So we want these to now be columns. So in other words, the initial condition would be for us y of y1, which is theta at the initial moment, is b theta naught. Y of 2, which is omega at the initial time, is omega naught. So the rows indicate whether or not I'm talking about theta or omega, and the columns indicate whether I'm talking about or what I'm talking about in terms of a time step. So j and I is the way to think about it. The first element is that of the equation. The second is that of the time step. So if we wanted to take this expression here and rewrite it, we would take the value that's in the variable name and move it in as the second index. So you can see y11, that's bringing this one over into the second spot of indexes. y10, bring this guy over into the second spot, and so forth. So what we've done now is constructed what is really a matrix, where you can see that the rows are in sequential order. What we're going to do is we're going to compute theta and omega for every time step in order. Theta and omega at the next time step, 1, is determined by theta and omega at the previous time step of 0. Let's make it explicit. So if we set I equal to 1, I is our time stepping index. You can see that it shows up in the second spot. So at y1 of 1, at the initial I equal 1 moment, this is the theta value. y2 at I equals 1 is going to be the omega value at the initial condition. So we've set that up. And now we're going to write down our two differential equations once again. The only difference is that we've replaced our values here for the time step up above with just I, or I plus 1, according to whether or not it's on the left-hand side or the right-hand side. So you can see that the I plus 1 value depends only on the Y values at the ith step, as you can see from the equation here as it's written in terms of these indices. The last thing that we want to do is to recognize that every time step we have to solve for every one of our values. So this is both row 1 and row 2. At I plus 1, we could write that using the colon operator. And that's indeed what we've done here. So let's write it one more time. Line 32 written again using the colon operator. We're going to have the colon here indicating both 1 and 2, theta and omega, at the initial time. I equals 1 is given to me by my y naught. And then we've got the y values for 1 and 2, theta and omega, at the ith plus 1 time step is equal to our vector value function f, evaluated at the previous time step, the yi time step, passing both values, and using those values into our function here that computes the derivatives and returns back the appropriate derivative for the first and second equations in each row, multiplying it by h, and then adding it together. So now I've got one equation here that does explicit Euler method for me. And this is really the first step in getting ourselves to a position where we can utilize the built-in numerical integrating routines. As I've written this right here, it's really ready for a loop since we've abstracted it in terms of this ith step. Let's go ahead and look. Here is a single code that kind of does the whole thing for the universal solution. We clean things up, we initialize things in MATLAB, but then we also tell the reader what is the first element of our solution vector and what's the second element, and then how do they relate in terms of the system of ordinary differential equations. This is quite independent of any time stepping. So these indices here indicate which variables I'm working on, which equations. We set up our time step, we have our initial conditions on theta and omega. We plug those into a single y naught vector here, and then we write our function that actually contains the derivatives in order for each one of my equations, using the derivative for the y1 variable, which is theta, and the derivative for the y2 variable, which is omega, written in order here in rows. So you can see they've just been translated down here. This is a vector value function, so I'm going to pass it y, which is a vector, and it's going to return a vector. It's going to return a column vector. After line 48, everything in this code is generic. Let me say it again. After line 48, everything after that could be used up until, I guess we would say when we're plotting things, could be used to do any ODE. And so it's really perfect for writing its own function at this point. And we'll do that next time. NE is the length of y naught, the length of our initial solution. And so that's the number of equations we're going to be integrating. NT is the number of solutions in time that we're going to have, and NT minus 1 is going to be the number of time steps. So we're going to subtract off that first time step because we actually know the solution at the first time step. We go ahead and initialize our matrices where y has two indices. The first, the rows, is determined by the number of variables I'm integrating, and the second is the number of time steps. NT is going to be the length of my t vector. We're initializing all of this stuff, and then we're going to go ahead and set up our initial condition. So at the ith equals 1 time step, we set all of the rows equal to their initial values, and we set our time equal to the initial time, and then we step through our loop. And we generate the solution at the ith plus 1 value of time using the value of the solution at the ith time. And this is the explicit Euler method. After we're finished with this, as we've seen, we'll basically have a big matrix that has two rows. The first row is going to be for theta and the second for omega. Each column will be the solution at a different time. And so it's actually easier to kind of work with the transpose of those things so that we can sprint out the time as a big column vector and the corresponding values of theta and omega also as a column vector. So we go ahead and take the transpose immediately after. We can put it in a table. We can also plot it very easily. And then the last thing I wanted to mention is that we could go ahead and reparticularize this for any pendulum of any length on any planet, so to speak. The only things that we've really fixed that are determinative for this universal solution are the initial condition on theta and omega. Those would have to be changed to generate a different, so to speak, universal family of solutions to get the complete picture. But nonetheless, we could use this solution to actually talk about any pendulum of any length. And in our case, if we were to take a pendulum of 1 meter, on Earth, we would have a time scaling of about 0.3193 seconds in order to see the effect of gravity to change the position of our pendulum. Here we can go ahead and actually just quickly redimensionalize our equations by multiplying by the characteristic time, and then we can go ahead and plot these guys. And this would be our dimensional solution.